Applications of Definite Integrals, Chapter 7. Are you tired of using logic and reason to solve simple math problems? Are you tired of reading or measuring to find the area or volume of a specific figure? If you answered yes to either of these questions, have we got a solution for you? Try calculus. Calculus is the way of the future. Calculus can best be described as a fun and difficult way to solve otherwise simple problems, and difficult problems too. Have you ever wondered how to calculate the volume of a cylinder not using v equals pi r squared h? With calculus, sí se puede. Let's see what calculus can do. One of the key concepts in Chapter 7 is calculating the area between two curves. To find the area between curves, you use the following formula, that being the integral from a to b of f of x minus g of x dx, where a and b are the limits of integration or the intersection points of the function. Here's a graph of what an area between curves problem may look like.
The first example will be of the area between x squared and x plus 2. First, we find the intersection points using a graphing calculator or algebraically, and we find that these graphs intersect at -1 and 2. This tells us the limits of integration. We use the formula from the previous slide to plug in the top function, x plus 2, minus the lower function, x squared, to the integral. We end up with the integral of the quantity x plus 2 minus x squared from -1 to 2. Using our integration methods, we end up with -3/2 x to the third plus x squared over 2 plus 2x. Plug in your right limit, subtract the substituted left limit, and voila, you get 9/2. Of course, you can always just plug that integral into your
Taught
calculator.
in Chapter 7 is calculating the volume of a figure using a cross-sectional approximation. To find the volume of a three-dimensional figure using cross-sections, you must follow these steps. First, you calculate the area of your cross-sectional figure. If it's a square, length times width, or if it's a semicircle, 1/2 pi r squared. You would then multiply it by the dx, which is the width of each cross-section. Finally, you integrate the figure from the leftmost intersection point to the rightmost intersection point. Here is an example of what a cross-sectional approximation may be.
A pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross-section of the pyramid parallel to the base is a square. Find the volume of the pyramid. We know that the base of the square has a length of 3 units. The formula for a of x is x squared because the cross-sections are x meters on each side. The limits of integration of the square are 0 and 3, as that is the height of the pyramid. We integrate to find the volume. V from 0 to 3, as those are the limits of integration, of a of x dx. X squared is our cross-sections, so when integrated, it yields x cubed over 3, from 0 to 3, which finally equals 9 meters cubed.
One final concept taught in Chapter 7 is arc length. You would use the arc length formula to find the length of a bent curve that you can't necessarily measure using the distance formula. The formula for arc length is the integral of a to b of the square root of 1 plus the derivative of the curve squared dx.
Our final example is an example of arc length. Suppose you want to find the length of the function 4/3 x cubed plus 2 for 0 to 1. First you find the derivative, which is simply 4x squared. Then you plug it into the formula from the previous slide, and you end up with the integral from 0 to 1 of the square root of 1 plus 4x squared squared. Simplify this, and then plug it into your calculator, and you get 1.8267. We hope this video was helpful and enjoyable. Good luck on your tests!